Hello, welcome to the wonderful world of physics. This is Physics 104, the Chapter 15 homework. Let's get into it with problem number 11. The density of molasses is 1,600 kilograms per cubic meter. Find the mass of the molasses in a 0.75 liter jar. So it's giving density and it's giving volume, and we need to find mass. So it's appropriate to think about this relationship. The density is mass divided by volume. We need to solve for mass, so mass is density times volume. We need to make sure we have consistent units. The units on density are MKS units, so kilograms and meters, that's fine. But volume is given in liters, so we'll have to make that adjustment. Let's plug in the values. 1,600 kilograms per cubic meter times 0.75 liters. Now we need to turn liters into cubic meters, recognizing that there are 1,000 liters in a cubic meter. So we put 1 cubic meter over 1,000 liters. The liters will divide out. We're left with a cubic meter in the numerator. And we multiply the numbers and we get 1.2 kilograms. Problem number 13. Compressed air with mass 8.8 kilograms is stored in a 0.050 cubic meter cylinder. What is the density of the compressed air, and what volume would the same gas occupy at a typical atmospheric density of 1.2 kilograms per cubic meter? Here's the given information. We have the mass, we have the volume, and it's asking for part A, what is the density given mass and volume? We'll do density as mass divided by volume, divide those numbers. You should get 176 kilograms per cubic meter. And given two significant figures, I'll round that to 180. The next question says, assume a different density, 1.2 kilograms per cubic meter. What would the volume of the same amount of gas be? So the same amount of gas means the same mass. Volume is mass divided by density, so we have a mass of 8.8 kilograms divided by the new density of 1.2 kilograms per cubic meter, and we get 7.3 cubic meters. Problem number 16. You unbend a paper clip made from 1.5 millimeter diameter wire and push the end against the wall. What force must you apply to give a pressure of 120 atmospheres? So the question is asking about the force, and it's giving us the pressure, 120 atmospheres. It is indirectly giving us the area over which the force is applied. So we'll start with pressure is force divided by area. Turn this into force equals pressure times area. So force equals, and we have the pressure of 120 atmospheres. But we want to turn all of this into MKS units, so let's recognize that an atmosphere is 1.013 times 10 to the 5th pascals, so we'll do that conversion. And this bit in the beginning, these two terms multiplied will give us the pressure in pascals. And then we want to multiply by the area. So it's a very tiny area, and we were given the diameter of 1.5 millimeters. It's a circle, so we'll do pi r squared. Be very careful of your units. We need this in meters, and so the diameter was 1.5 times 10 to the negative 3 meters, but this is the radius, so cut that in half, 0.75 times 10 to the negative 3 meters. Be sure to square it, and in the end you get 22 newtons, which is about 5 pounds. Problem number 17. What is the density of a fluid whose pressure increases at the rate of 100 kilopascals for every 6 meters of depth? So it's asking the density. It's giving a rate of pressure increase per depth. And so this brings to mind this equation right here. There's the rate of pressure change per depth. dP over dH is rho g. And so we want to solve that for density. Let's divide both sides of the equation by g. And I did a left and right side of the equation switcheroo here. So now we have density is 1 over g times dP dH. And again, dP dH is the rate of change of pressure. Plugging those numbers in, we have density is 1 over g, so 1 over 9.8 newtons per kilogram. Pressure change per depth change, we'll just do, it's at 100 kilopascals. Well, a pascal is a newton per meter squared, so let's call that 100 times 10 to the third newtons per meter squared per 6 meters. So divide by 6 meters, and you should get 1,700 kilograms per meter cubed. Problem number 20. A vertical tube open at the top contains 5 centimeters of oil with density 0.82 grams per cubic centimeter, floating on 5 centimeters of water. Find the gauge pressure at the bottom of the tube. The gauge pressure is going to be the pressure that the water contributes plus the pressure that the oil contributes. Now, there is an absolute pressure, and that is the pressure from the water plus from the oil plus from the roughly 60 miles of air up above. The gauge pressure then is all of that minus the pressure from the air. We go to this basic equation right here that says that the pressure at the bottom of some fluid is the pressure that is being pushed onto the surface of the fluid plus the density of the fluid times g times h. When we apply this equation to position P1 at the bottom of the oil, we get that P1 is the pressure on the top of the oil, so that is P of the atmosphere. That's what I've written in the picture as P naught, but we can call that P of the atmosphere, plus the density of the oil times G times the depth of the oil. The pressure at the bottom of the water is, and again, we're just applying the equation at the top, it's the pressure at the top of the water, which is P1, plus density of the water times G times height of the water. Now, let's substitute in for P1 what I did on this second line up here, pressure from the atmosphere plus density of the oil times G times H of the oil. So when we take this P2 equation and we substitute in for P1, we get that P2, the pressure at the very bottom of the tube, is pressure from the atmosphere plus rho oil G H oil plus rho water G H water. The gauge pressure is going to be all of that minus the atmospheric pressure. So here at this line where my marker is, P2 minus P atmosphere. So the gauge pressure, which I've denoted as delta P, is what you see up here, P2, but minus the atmospheric pressure. So it's going to be rho oil GH oil plus rho water GH water. We can factor out the G, as I've done over here. And now let's plug in the values. So we have G, which is 9.8, times density of the oil, 0.82 times 10 to the third kilograms per cubic meter, times 0.05 meters, plus 1 times 10 to the third for the density of water times 0.05 meters, and you end up getting 890 pascals. Problem number 21. A child attempts to drink water through a 36 centimeter long straw, but finds that the water rises only 25 centimeters. By how much has the child reduced the pressure in her mouth below atmospheric pressure? The 36 centimeters in the question that's first stated is completely irrelevant. All that matters is that there was a change in pressure, and that change in pressure in the child's mouth led to a rise of the water of 25 centimeters. We have these equations here that the pressure in the atmosphere pushing down on the fluid, which therefore pushes it up the straw, is equal to the pressure in the mouth plus rho GH. So the difference in pressure, the question asks, by how much has the child reduced the pressure in her mouth? Well, at first, the pressure in the mouth was just atmospheric pressure. So we're looking for that difference right there. P atmosphere minus P mouth equals rho GH. Or as I've written down here, delta P is P atmosphere minus P mouth over rho GH. So we can plug in those values. We can say delta P is the density of the water, 10 to the third kilograms per cubic meter, times 9.8 times 0.25 meters, and we get a difference of 2450 pascals. Now, we can also answer the question in terms of by what percentage of the atmospheric pressure. So let's take that 2450 pascals that she has reduced the pressure in her mouth, divide by atmospheric pressure, 1.013 times 10 to the fifth pascals, and we get about a 2.4% reduction in pressure. Problem number 26. A steel drum has volume 0.23 cubic meters and a mass of 16 kilograms. Will it float in water when filled with A, water, or B, gasoline, which has a density of 860 kilograms per cubic meter? So what we want to evaluate in these two separate cases is the question, is the total density, the steel drum plus whatever fluid is in it, greater or less than water's density? That is what will determine whether or not it will float. Now, before we get into any math in part A, if you just think about it qualitatively, it's pretty obvious that it should sink if it's filled with water. It's already made of steel, plus it's filled with water. So overall, it's more dense than water. It will sink. Part B isn't obvious. The gasoline has a lower density than water. It might sink or it might flow. But I hope you can see that in part A, if the steel is filled with water, it will sink. Well, let's actually do the math. The density, and we want to see is it greater than 1,000, is mass divided by volume, total mass. I've used a capital M there. So what is the total mass? It's the mass of the drum plus the mass of the water divided by the volume. So we have mass of the drum plus, now we're not given the mass of the water, but mass of the water is going to be density of the water times volume of the water. So let's plug in the values. We have the mass of the drum, which is 16 kilograms. We have the density of water, 1,000, times the volume, 0.23 cubic meters, divided by 0.23, and we get 1070 kilograms per meter cubed. It's greater than 1,000, so it will sink. Interestingly, if you just look at what I'm circling here with my marker, this bit in itself would come out to 1,000. That is just the water itself, which would not sink or float. It's perfectly the density of the water that it's the surrounding water. Anything you add to the numerator, such as this 16 kilograms, is what makes it sink. So the steel is what makes it sink. Let's go to part B. I'm going to take this equation up here where my marker is and just apply the density of the gasoline instead of water. So we have 16 kilograms plus 860 times 0.23, divide by 0.23 cubic meters, and we get a total density of 930 kilograms per cubic meter. Since that's less than 1,000, it's less than the density of water, it will float. Problem number 27. Now we're getting into fluid dynamics, moving fluids. It says water flows through a 2.5 centimeter diameter pipe at 1.8 meters per second. If the pipe narrows to 2 centimeter diameter, what is the flow speed in the constriction? So it's not narrowing by that much. It's going from 2.5 centimeters to 2 centimeters. It's narrowing a little bit. So we expect there's going to be a little bit of increase in the speed. When it gets narrower, there's an increase in speed. What's appropriate is the continuity equation. Cross-sectional area 1 times V1 equals cross-sectional area 2 times V2. And then it's a circular pipe, so we'll say pi R2 squared V2. I've done a switcheroo left and right side because I want to solve for V2. So pi R2 squared V2 equals pi R1 squared V1. The pi's divide out. When I solve for V2, I get R1 over R2 squared times V1. And we could plug in the values just like that. It requires taking diameter and dividing it by 2. But the neat thing is, if we're going to take diameter and divide them both by 2, it's the same ratio. So you could divide the diameters by 2, but you could recognize that the ratio of the radii is the same as the ratio of the diameters. They're just both off by a factor of 2. So I've turned this equation into d1 over d2 squared times v1. So we have 2.5 centimeters over 2 centimeters. We're going to square it times 1.8 meters per second. And it's 2.8 meters per second. And it's good to evaluate this. Remember at the beginning, as I was qualitatively evaluating it, I said that since it narrowed a bit, we expect a bit of an increase in speed. And here we see it has indeed increased in speed. Problem number 31, a bit of physiology here. A typical human aorta, the main artery from the heart, is 1.8 centimeters in diameter and carries blood at 35 centimeters per second. Find the flow speed around a clot that reduces the flow area by 80%. All right, so very dangerous for our blood vessels to have clots. And here you can see a picture. This is the cross-section of a normal blood vessel. And this is the cross-section of a blood vessel clogged with cholesterol deposits. So that's very bad, and it'll lead to an increase in speed. All right, we get the continuity equation A2V2 equals A1V1. It's asking to solve for velocity, so let's do it. We don't directly have the areas, but what we do have is that in the problem, it says the clot reduces the flow area by 80%. And that means that A2 is 20% of A1. And that's enough information to get through this problem. So let's continue with the continuity equation. V2 is A1 over A2 times V1. Now let's do a substitution. Since A2 is 0.2 of A1, let's substitute it down in there. The A1s will divide out, so it didn't matter to us what exactly the area was. All we needed was that ratio between A1 and A2. And this leaves 1 over 0.2 times V1. So now we have, let's plug it in, we have 35 centimeters per second divided by 0.2, which means the flow speed is being multiplied by 5. 175 centimeters per second. Because we only have 2 significant figures in the given information, let's round that, so 180 centimeters per second. Problem 35 comes from example 15.4 in the book. So before approaching this problem, you might want to go back and review example 15.4 with the iceberg above the water. Let's do it. It says lakes on Saturn's moon Titan are filled with liquid hydrocarbons, largely methane, but also some ethane. Suppose scientists want to send a probe to explore Titan's largest lake. The probe is to be a cylinder 56.3 centimeters in diameter with a mass of 135 kilograms, and it's supposed to float with the long dimension vertical, half submerged and half above the lake's surface. If the liquid in the lake has a density of 482 kilograms per cubic meter, what should be the probe's length? All right, let's think of the important information here. We're given the dimensions of the cylinder, the diameter, the mass. We are given the density of the fluid that it's going to be in. And it says it's supposed to float with the long dimension vertical. It's also useful to note it says half of it needs to be submerged and half of it needs to be above the lake surface. And so what should be the probe's length? Well, it helps to first draw a picture of what we're dealing with here. There it is, the probe, and some of the given information that I've written out, and half of it is above the surface and 50% of it is submerged. We are looking for the dimensions of the probe, which has to do with the volume of the object. So this should bring to mind, especially if you've reviewed example 15.4, this equation right here, that the volume submerged of an object that's floating divided by the volume of the object is equal to the density of the object divided by the density of the fluid. And that's enough that we need to get us through this problem. Now the density of the object over density of the fluid, as I've written here, needs to be 50% because that is the percentage of the object that needs to be submerged. So let's take this and say the density of the object needs to be 0.5 times the density of the fluid. And we need now to figure out the dimensions of the object given that density. Well, let's replace density of the object with its mass over its volume. And if it's half the density of the fluid of the lake, that would be 241 kilograms per cubic meter. And let's do some algebra here. And now we have volume of the object is equal to the mass of the object, which is 135 kilograms, divided by 241 kilograms per cubic meter. So that is the volume of the object. I've calculated that and I get 0.560166 cubic meters. Now we need to know the length of the object, not just the volume. So let's divide up volume. It is a cylinder. Let's divide it up into pi r squared times L. And we're going to solve for L. So taking this equation, solving for L, we'll divide both sides by pi r squared. And make sure you turn radius into meters. At the top of the screen, it's given diameter in centimeters. Let's divide it by 2, turn into meters. And you should get a length of 2.25 meters. Number 54. A newfangled swim float, the Max Raft by Watermat, measures 1.8 meters by 2.4 meters and is only 10 centimeters thick. Its mass is 20 kilograms. How many 50-kilogram children can the float accommodate before the water comes over its top surface? Assume the float stays perfectly level. Well, let's draw a picture here. You see the raft, and it is completely submerged. Based on what the question asked, the water just comes up to the top surface. So it's completely submerged. It can't be any more submerged because then we have to account for the feet of the children displacing water and buoyancy being added from that. So we're looking at that the children are not displacing any water, but the raft is entirely displacing water. We're going to need information about the mass of the children and the mass of the raft. So I've used little m for the raft, big M for the children. And let's draw a force diagram of this entire system, which is the raft plus the children. Buoyancy force is pointing up, gravity is pointing down, and the gravity on the entire system is the total mass, so big M plus little m times g. With that, let's apply the sum of the forces equals 0, so it's in static equilibrium, just floating. Buoyancy force upward minus big M plus little m times g equals 0. And let's do some substitutions. Let's first get the m plus m times g over to the right-hand side by adding it. Buoyancy force, let's replace that with density of the water times volume of the water times g. And once we do that, g can divide out of both sides of the equation. The question is asking how many children will this accommodate? And each child being 50 kilograms, we're assuming. So we want to solve for the total mass of children. That's big M. So from here, it's just algebra. We'll say density of water times volume of water minus little m equals big M. And now let's plug in all the values. Density of the water is 1,000. Times 1.8 meters times 2.4 meters times 0.1 meter. That is the volume of the raft, and it's also the volume of the water displaced. So that's the function it's serving in this equation here, minus the mass of the raft, 20 kilograms. We plug that in, and we see that it can accommodate 412 kilograms worth of children. Divide that by 50 kilograms per child, and we get 8.24 children, and so it will accommodate 8 children. Problem number 66 says water emerges from a faucet of diameter d0 in steady near vertical flow with speed v0. Show that the diameter of the falling water column is given by d equals d0 times the 1/4 power of v0 squared over v0 squared plus 2gh, where h is the distance below the faucet. So this water, as you can see in my picture, is the column is going to get narrower and narrower because by the continuity equation, it's going to be going faster and faster and therefore getting narrower. So let's start with the continuity equation. A1 V1 equals A naught V naught. And the area of the column is pi R1 squared times V1. And the area of the column at the top of the faucet is pi R0 squared V naught. The pi's divide out. We want to solve for R1. We actually want D1, but the way to get there is to get the radius. So R1 becomes R0 times V0 over V1, the square root of that. So hopefully you can go through, it's about 2 steps in algebra. You solve for R1 squared and then take the square root, and you should get that. Now, if you multiply both sides of the equation by 2, you get diameter, because the question is asking about diameter. And so just multiply both sides by 2. Now it's D1 equals D0 times V0 over V1 square rooted. And at this point, we need to think about the free fall of an object, the free fall of that water. So remember back to our kinematic equation that V1 squared is V0 squared plus 2gh. So we're going to make that substitution in the denominator. And what we need to do, you notice that at this line, the D1 line, it's got V1. But our kinematic equation involves V1 squared and V0 squared. So what we can do is before we apply the kinematic equation, let's turn the diameter equation into something involving the velocity squared. So what I'm doing from this line to this one line is I'm squaring everything in the parentheses and then taking the fourth root. So essentially, as this exponent is 1/2, I'm making it 2/4 down here and applying that 2 to the entire parentheses. And so now it is V0 squared over V1 squared to the 1/4 power. And now I can make that substitution in the denominator. V1 squared is V0 squared plus 2gh. And there you have it, what I've written out typewritten, and that is what the problem asked us to solve.